Programming data structures, or inventing a machine that is already old and wrong. I recall some expert giving his opinion on the work of a young researcher that went something like, "All the new breakthroughs they claim to have made are old, and everything else has been proven wrong." I think this is lovely, and I'm sure the expert was wrong and probably off his head. And the loveliness comes from the fact that the young researcher was independently reinventing things, becoming as wise as the original inventors, and being able to see all the paths they didn't take. The old guy was wrong, and the young researcher probably changed the world. Let's jump right into it, as the introduction would take many hours, and I primarily want you to know what data structures feel like, what the gibberish sounds like. To give a sprinkle of background information, programmers have variables of type number and text, called strings of letters, and then many of them don't realize that they have bucket variables. Those are objects and lists, here called arrays. And I call them buckets because they can hold other variables of any type. In low-level programming languages like C, a string variable is pretty much a bucket because it is an array of numbers that represents letters. But we are working with JavaScript here, on a higher level, where we can just put some text in quotes and we simply get a string variable or a text variable, not some array of whatever. Now, this being the modern world, we want arrays to announce when they have changed. This is why we are using a high-level programming language. We don't want to be tripping over type definitions and low-level concepts and limitations, because what we are doing is already pretty messy. Let's say our array holds a list of people, and that list can be updated by the server and from the user interface. There are many crazy ways that programmers try to tame this. Event emitters with wildcards, immutable data structures, alcohol. But we want to be revolutionary here. Our array will emit a single message when something is added or removed. It will tell all the things interested in it, "I changed." If we tracked added and removed, which seems pretty efficient, our interface would need to do two different things to update. But we are not going to be efficient at this level and send only a notification of change. And that will mean our user interface will have to rerun itself to update and nothing more. There's room for optimization here, because our list will always mark entries with a unique ID, so when the UI is re-rendering, it can compare ID numbers to see what has been removed or added. But computers are fast, and we want to keep our code clean, and encourage our coder to use a templating engine like Svelte, which will look at the ID and automatically optimize re-rendering of the user interface. So now, when we add or remove a person, the array announces, "I changed." Let us call our array a table to make it sound special and friendly and professional, and give our table columns for integrity. ID, first, last, and age. We want to keep the same ID at all times, but first, last, and age can change. And just like with the array, we want to emit a single message. I changed. We are not going to emit deleted or field empty or error in the field, just changed. So with 3 users in our table, we have 12 fields containing ID, first, last, age. The ID field does not support changes, so we only have 9 fields that announce their updates. And all of them just emit a single message. I changed. Let's say we have Alice Smith, age 101, Bob Smith, 99, and Carol Smith, age 50. And now we create a report with people over 100 years old. In our case, that will be Alice. And this is a tall order because we have to monitor the table for when it changes, and we also have to monitor age column because that will get updated as well. When it comes to the report, we only pay attention to the fields that are pertinent to the report itself. First name and last name are important, but their changes are kind of automatically handled once the data ends up in a user interface. So we are monitoring 3 fields and the array. And then to make our report, we rerun it at any of the 4 changes. Our filter for creating the report simply says report.filter equals table filter person.age greater than 100. This is pseudocode, but a special part of our system because the person object here is not exactly the person in our table. We are using an object proxy to intercept what is being used in the filter, age in our case. And now we will know to subscribe to it automatically. It's basically automatic dependency resolution. So we listen to the age to rerun the function that filters the original table, and automatically update the report, excluding or including new people. And we are already listening to the table. So our old and wrong and inefficient software machine creates a report that updates itself whenever its sources change. And as with everything else, the report will emit a change event as well. So now we can use this report as a source for a new report. And for example, return all the last names of really old people. What this really means is that we can chain reports, filtering down and manipulating data as necessary. This is just about 10 lines of code, but we get automatic dependencies and updates. Hidden here is the mechanism for unlistening to free up memory. It will be a stop function that once called will call all the dependencies to stop them as well. We have tables that create and update other tables, reports. Let us give them order. Let us file them in some logical thing. Let us go wild and say, object type folder has an array called folders. And this actually creates a tree. We make a root folder called application and add a folder called users, and add the users folder to applications folder array. So it's a recursive data structure made up of folders. We can nest things like this to no end, creating an entire application hierarchy. Once we have a tree that makes sense for our application, we can then attach tables in various spots wherever it makes sense. And we can make a new array inside the folder called tables, or just throw them into the folders array. Very similar to how files work in a file system. Now we can sort our reports. We can talk about people and users and various other things throughout the tree. And then we can call tables from other places in the tree. But which is more, we can map out the user interface with the tree. Application folder would have a window. Window would have a side pane and main pane. Main pane would have a list. A simple UI system like Svelte can crawl data structures like trees with a for each loop. So our window having a side pane and a main pane means we have two entries in the Windows folder array. And that means the for each loop would scan window.folders and first render a component for side pane and then a component for the main pane. We can't change the folder array to a report, and the for each loop would rerun, making the UI dynamic. But our aim here is to use the for each loop with the users over 100 years of age report. Our one-line tree and 10-line data machine will alert the for each loop when the report changes, efficiently updating the UI representing a person. But also at the same time, if only the person's age changes in the original table, the UI will just update that number alone without rerunning the efficient for loop in Svelte. Unfortunately, it is not possible to go into greater detail, but there really isn't much more to add. It's a pretty robust data structure and rendering method. We have a tree with tables and reports that self-update, and use Svelte to efficiently decorate our data tree with user interface components. Svelte programmers would notice here that components don't have to extract data because all of the calculations happen in the tree and the tables. This way, user interface components can just deal with clicks and fields and list updates. And the low-level or low-ish level programmers would notice scary things here, because their programs demand discipline and force them away from dynamic UI stuff. It's difficult, if not ridiculous, to try to create dynamic user interfaces in more strict languages. For the rest of us, we shouldn't really feel bad that we only emit change events. These tables never hold more than a screenful of stuff. My own precise use case is color gradient creation for a fantasy user interface. My tables will rarely have more than 5 items. And my tree does use tables for other branches, so in my case, the very structure of my tree also announces change, and the UI efficiently updates. Programming only gets complex when programmers don't know the vision of a program. Imagine someone, quote, optimizing, unquote, our report to emit more than change. We lose that pretty simplicity, and if someone removes the tree thinking that it was useless and out of place, we can no longer decorate the tree with user interface components. That now has to become its own tree. And it all gets even more complicated from here. Few programmers optimizing one on top of the other over a stretch of years would completely complexify this application, and the code would become unreadable and need unit tests and probably an office of old men that wag their fingers. Reinventing what people tell you has already been proven to be wrong or has been done better is a magnificent way to explore and learn and become an expert. And being inefficient is quite the powerful act during reinvention, because those are the paths that the original inventors omitted, thinking that they are suboptimal. But as the case is with rendering, you can calculate if you are adding or removing based on whether the ID is there or not. It's a quick check, not at all inefficient. Lastly, I invite you all to ask your favorite AI to create a minimalist JavaScript signals implementation and talk about the object-oriented version and how signals help in general and their subscribe-unsubscribe lifecycle, and try to create some simple little programs and maybe even a tree